And
Okay, hi, thank you everyone for joining, both in person and remote. It is my pleasure to introduce Eddie Berman today. So Eddie is an undergraduate student at Northeastern, majoring in physics and math. And he has been working with us on one of our AstroAI projects, the biomarkers in exoplanet atmospheres projects. He's been doing a lot of work on uncertainty quantification, Bayesian analysis, and retrieval of molecules of biomarkers in exoplanet atmospheres. He's working with Robin Walters in Northeastern, and he's also been working with the cosmology group in Northeastern with projects involving web data. So I'm very excited to hear what Eddie has to tell us today.
Thank you so much for the introduction. I'm really excited to speak. So you mentioned, yeah, I'm undergrad and with Robin's group and as well as the zoology group with Professor Jacqueline McCleary and Jonathan Lazik. And today I'm going to be talking about uncertainty calibration for equivariant functions. I'd also like to take a second to present some of my collaborators. Here on the Northeastern side, I'm working with Jake Janessen, who's here on the left, and I'm advised by Professor Robin Walters, who's here on the right. And I'm also very grateful to be collaborating with AstroAI, who being hosted today for the biometrics collaboration. So yeah, I couldn't be more thrilled to get on with the subject of my talk. So as a start, I'll talk about a little bit of a motivation with everybody's favorite board game, tic-tac-toe. So you can see here on the top, we have like a tic-tac-toe board, and you have some function here in the middle that's predicting, what it thinks is the best move to play. If you're the circle to move, you want to go on the bottom right because if you don't, you lose. And maybe we're also pretending that our input data is the picture of the tic-tac-toe board, which has some noise, because we have an uncertainty map on the right. And the linchpin of equivariance, the reason we care about it is that when we rotate the input, the tic-tac-toe board, our outputs, the Q values here, and the uncertainty estimate, rotate along with it in the exact same way. So that's what a means for a function to be equivariant. Rotating the input, essentially the same as rotating the output in this way. So more formally, equivariance is a property of a function that allows us to reason about a group symmetries in something like a neural network or beyond. It could just be any function. And it's shown that through the literature that the equivariant function neural networks are more sample efficient. You don't need as many samples to train them because they automatically generalize across your group symmetries. They're also more parameter efficient in part because the way we achieve equivariance is done through weight sharing, and as well as the sample efficiency coupled with that. You just don't need as many parameters to train it as you would a non-equivariant counterpart. And so a question you might ask, is it also more calibrated? Where calibration refers to the sort of disagreement between the model's accuracy and its predicted confidence. So we know that equivariance has been helpful in all these sort of data-sparse regimes, but in these data-sparse settings, we usually care about model calibration. And so the question is, can equivariance help us be better calibrated? And preliminary work would actually suggest yes. There are some experiments in the literature. In this example, where you're having a car and it's trying to figure out the best route to navigate through the street. And we're also not only considering the best route, but some sort of uncertainty estimate on where to go. So maybe I'm supposed to go straight, plus or minus however many feet in each direction. And here, this work PECO, which is the algorithm, it's a paper from one of Robin's groups. They made it equivariant so that if you rotate the input map, then your input trajectory changes in the same way. But a surprising result wasn't just that it was more accurate, it was also more calibrated. So there are signs in the literature that we should be paying attention to this. And to try and be more precise and to try and get to the truth of whether or not this is actually holding in general, or is it just a product of our specific use cases? Is it just coincidence from a couple of examples? So in order to answer this, we're gonna have to be even a little bit more formal about what it means for something to be equivariant. So I have up here the strict definition of equivariant. It's a property of a map or a function between vector spaces. Vector spaces X and Y respectively, and you're equivariant with respect to a group G, and you're equivariant if for all elements in your group G, the function commutes with the representation of the group action. So if I have my input X and I act on it with the representation of my group and then apply my function, that's the same as applying my function and then rotating my output. For an example, this could be a rotation. So maybe I have like a molecule given by its position that it emits something like a force vector. So I want to predict the force vector. So predicting the force vector and then rotating it is the same as rotating the input molecule and then putting it through the function. A special case of this is invariance. You achieve this special case in which the representation of the group action in one vector space Y is just the identity. Essentially, when you put the function through F, you go from one vector space to another. So the representations of your group action or your rotation matrix, for example, need not be the same. And so in this case, your special case of invariance, any group symmetry that you put on your input will give you the same output. So everything within your orbit GX will give you the same output. And this is typically really useful for things like classification tasks, where maybe I have a picture of a galaxy and I want to guess what kind of morphology it has. If I rotate it, it's really the same elliptical structure. So yeah, I've been sort of alluding to them, but to give some more examples, we have the galaxy morphology classification, which has E2 classification invariance. So if I rotate or translate or reflect any of these images, it should give me the same morphological class. So we have example pictures from Galaxy View dataset from the Sloan Digital Sky Survey, SDSS, and the Dark Energy Spectroscopic Instrument, DESI. And we have these classes about what kind of morphology class we want. And the idea is, maybe take, for example, the smooth cigar. If I rotate the image of the smooth cigar in any way, it's still a smooth cigar. So I better hope that my molecule, my function gives it the same class. So this was, to reiterate, E2 classification invariance. And then another example would be E3 regression invariance. So here, the input data is the position of your molecules in three-dimensional space. It's just the positions of each atom. And if I rotate them in any way, I want to get the same spectral line as an output. And in keeping with the theme of this talk, we're not just outputting a spectral line, we're also outputting an uncertainty estimate on that spectral line. And this should obey the same invariance as the prediction itself. So if I rotate the molecule in any way, I want the same spectral line and I want the same uncertainty estimate. I want both. And returning to the example from the beginning of this talk, we can think of things in pick and place robotics. Here we have tic-tac-toe, but you'd be amazed about how many modern robotics research problems actually can boil down to this. You have a 2D grid, you have some state that you're in an action you want to perform. Here we have a state of a tic-tac-toe board, and the action is playing the next move for the blue circles. And we want the action to rotate along with the board. So again, if we rotate the tic-tac-toe board, the relative values of putting the circle in each location change, and sort of the uncertainty estimates. We'll see that in the top case, the best action is the move in the bottom right. If I rotate the board, the best action is from the bottom right. And there's obviously going to be zero reward for placing, a circle on something that's already placed, and so on and so forth. So we talked about equivariance, and the goal for this talk is sort of marrying the ideas of equivariant functions with uncertainty estimates. So So at this stage, we'll be giving a little bit of a primer on uncertainty, and specifically the idea of being well calibrated. Where I said before, it alludes to the disagreement between a model's accuracy and predicted confidence. So formally, you have sort of a ground truth classification given by f from x, your input, to your labels y, and you have a set of functions h that you're using to approximate what the ground truth is f. And so for normal classification tasks, this normally amounts to just enumerating all the possible factors you have and outputting a distribution over some labels. And so the idea here is we're also using the information in the logic. We're not just looking at what the maximum probability is and what the label that corresponds to. We're looking at how much probability is given to that class itself. And giving this motivates the sort of definition of the expected calibration error used for classification tasks. It's the expected disagreement between your accuracy and your confidence. So the read of this is sort of saying my model has confidence P. Given that it's confidence P, how accurate is it? And so the intuition here that if I'm 80% confident, then I should be 80% right 80% of the time. I think it's worth noting that a model can be well calibrated, but also not performant. It might only be right 50% of the time, but it could know, hey, I don't know what's going on here. I don't know which class there should be, and it predicts its confidence at 50%. And we can do sort of analogous things for regression. Now our model class isn't going from X to Y, a set of labels. It's outputting a mean and a variance, sort of the simplest sort of the simplest way to parameterize some sort of distribution to give you an uncertainty estimate, which is just whatever the variance is. And we'll say that we're well calibrated if the error between my mean prediction and my labels, the squared errors are around sigma squared, which is sort of, by definition of the variance, your square difference from the mean should be about sigma squared. And so we want any time the model predicts a variance of sigma squared, its mean squared error should be roughly that. So equipped with these notions of uncertainty, we now wish to understand how equivariance, or in a specific case, invariance, from a model class H can affect our calibration. Specifically, we want to talk about, we want to reason about this in terms of upper bounds, like how badly can we be miscalibrated? I'm not going to go through all the cases of classification in equivariant regression. I'm going to instead focus on invariant regression, and then we're going to go through together an example applying this on a case study of chemical spectra. So yeah, as I said, our first goal is to see if we can come up with some sort of upper bound for a class of functions H that are known to be invariant with respect to a group G, and nothing else about it. We know that it can be arbitrarily expressive, but it has to be invariant. So a little bit of a proof sketch for this. The intuition here is that if you have like an error vector, this is just the mean squared error, and you're looking at the difference between the variance, and you're taking this L2 norm squared, so just the squared difference between each of these guys. Well, because the variance is going to be positive, and the error vector is going to be positive, this will be less than this quantity. So in some way, the calibration error is related to the regression error. So the higher, or if we have a really low, if we have a really small lower bound on the error, that gives us a tighter upper bound on the calibration. The other sort of piece of intuition I'm going to give is that if you're considering orbits, individual orbits on the domain X, you can sort of reason about all the things on your orbit that give you a specific variance. So specifically, if my model predicts a variance on X to be a vector that I'm going to be being sigma squared, then sort of by the definition of invariance, everything on that orbit will give me the same sigma squared. So we can sort of decompose our error onto individual orbits that correspond to variance predictions. So yeah, instead of formally, every variance predicted by the model corresponds to at least one orbit in the domain X. So yeah, at a high level again, we bound the calibration error by considering the regression error on individual orbits induced by sigma squared. And indeed, this is sort of what the upper bound comes out to be on the calibration error for the invariant or equivariant function. Here we're taking the expectation over sigma of the regression error, given that your variance is sigma. So I'll go through an example and we'll sort of walk through this together. Essentially, you look at all the orbits that give you a regression error of h on sigma squared. So yeah, this will hopefully be a lot more clear as I go through our case study here on chemical spectra. I'll also I'll note that this is a fabricated example. The sizes and positions of each of the molecules are not exact as you would find in Q9. I'm just giving them, X, Y, Z coordinates for the sake of example. So I ask that you hold a suspension of disbelief on the molecule that I'm about to present to you. So in full, our example looks like this, and we're going to end up breaking this sort of down row by row. But the idea is I have 5 molecules in my data set. One is methane like this in a sort of plus-like fashion, and the other is the same methane particle sort of rotated. And then here we have a water molecule and a sulfur dioxide molecule. They don't give the same spectrum because they're different molecules, but in terms of the relative shape, they look quite similar. And then the bottom, we have an ammonia molecule in its spectra. And then finally, we have an input probability density of getting each of these molecules in our data set. So in other words, I might have twice as many carbon atoms as I would a hydrogen atom. Specifically, we're saying that there's a 50% chance that you get your ammonia molecule, and then among that, you're equally likely to get any of the 4 molecules up above. So let's focus on this top row for example. And remember that I'm saying, sorry, I'll point out one more thing. The last thing I'll point out to you is that these molecules, these top 4, produce the same variance vector. And so the upper bound, if we look at all the things, we have 2 distinct orbits that give this variance vector. So the regression error restricted to all the inputs x, it can be a variance this, is going to be sort of an average of the error on the first row and the error on the second row. So on the first row, our invariance claim is sort of correct because of the same molecule. If I rotate my methane, I can get the same spectra. So the ground strength is constant. So if I assume that h is constant on that orbit, I should be able to fit it exactly. But on this one, we sort of concocted this sort of adversarial example. The water and sulfur dioxide molecules do not emit the same function, but they're the same up to sort of this E3 or E2 invariance. And since I assume that my function is invariant to these positions, it has to be constant on this orbit. So the best that we can really do is the average of the spectra between hydrogen and sulfur dioxide. The best I can do is sort of the average of the function f on the orbit gx. So we're taking the weighted average of the probability of landing in either of the orbits. The orbit before is we were equally likely to land in this guy when we were sampling from our data set as we were in this guy. So essentially it's 0 times 0 error from the first guy, and then 1/2 times the total area here is what's going to contribute to our upper bound on the calibration error. And then sort of similarly here, we only have 1 input molecule, so we can fit the spectra exactly using an invariant model. So we're going to get 0 calibration error in here. So yeah, so looking at it at the big picture, if we're essentially just taking 0 times whatever error this is, 0 times whatever probability this is, so 50% of being within this ammonia molecule, and then 0.5 times the total error in your fit from this guy, assuming that your model is getting as good as possible of a fit. So this is a nice interesting case study on spectra, but at this stage we want to go from theory to practice. We want to train an equivariant model, predict a spectral line and an uncertainty estimate using 209S molecule. And the goal here is to show that our bounds can be realized in a more realistic setting and not just on sort of these arbitrary molecules that I've concocted and drawn on the board, which are not realistic. So due to binning approximations, this can be quite hard. Recall before that we were taking an expectation value over sigma, and sigma can take anything on the real line or the positive real line from 0 to infinity. So at some point, I sort of have to bin the possible variance vectors that I can get. And this can cause really annoying things to happen in practice. For example, people have shown that you can have a correlation with your calibration metric with the number of bins that you use, which is obviously an undesirable artifact if you're trying to fit something exactly. You don't know which binning approximation to trust, so to speak. But the great thing about a result is that regardless of the binning approximation that we make, we find that our bound is satisfied. So on the the bottom, we compute, we train our E3 invariant model to produce the spectra, and we calculated the calibration error on it, and we show that it is strictly less than the upper bound. So this does a couple things for us. It shows that we didn't really make a mistake in our memo. It shows that when we restricted our error over individual domains and we sort of averaged that out, that actually works to obtain your upper bound. Yeah, that's the main thing it does for us. And it also shows that it can be somewhat useful to a practitioner who's looking to train a model, gauge whether or not what they're doing from this before they even start, can produce something that's well calibrated just by considering the group actions on their data set. So yeah, that's the main result of the case study. But we've definitely been exploring uncertainty equivariance on multiple different axes, which I'm now going to go through in some more detail. So the first thing we'll talk about is sort of a taxonomy of equivariance types. I sort of alluded to this when I gave the example of the chemical spectra. When you rotated the two rotations of the methane, they rotated onto one another and they produced the same spectra. But then I showed the water molecule and the sulfur dioxide, and I showed, oh, they actually gave a different answer. But because they could rotate onto one another, they were forced to give the same answer by our function approximator h. And so you can sort of reason about these equivariance types in sort of this correct versus incorrect way, as shown here with these Swiss rolls. So the idea is I'll return to this image in a second, but the idea is to predict the color blue or yellow from the position x, y, z, and we sample in different proportions from the correct or incorrect Swiss rolls. So you can see here in this sort of incorrect case, if you have a model that's invariant to whatever the z-axis is, then you won't be able to tell the blue from the yellow because they get mapped onto the same color when you squish the z-axis. But for the correct, it's actually helpful because the ground truth color is invariant to whatever the z-axis is. When you squash the blue, it goes on to the blue. When you squash the yellow, it goes on to the yellow. And so it was shown as sort of an adversarial example in a paper that this can lead to detriments in your model performance if you sort of incorrectly impose a z invariance. And the way we sort of extend this is we show that this similar thing is true for the calibration error. As you increase the amount of data that comes from the correct Swiss roll distribution, your z invariant model here in blue slowly climbs to the performance of the MLP. And conversely, it becomes better calibrated. And you might expect this inverse trend to happen, but I'll note that this need not be the case. It says something about the model actually being certain. And in fact, later on, we'll see an example where your accuracy increases, but your calibration doesn't have an effect. So the point of this is to show how incorrect sort of equivariance of your model, not only will it affect how well your model can perform in terms of accuracy, can also affect how well your model performs in terms of how able it is to predict its own confidence. And sort of as I just alluded to before, here's an example. I showed the SDSS and DESI galaxy morphology class service one before, and here we're showing that sorry, I'll shoot back up a second. We're approximating the E2 invariance in the classification task using discrete subgroups, sort of just cyclic rotations, so up to 4 or up to 8. That's sort of what the x-axis is here. And we're showing that as we increase the number of symmetry in our modeling by increasing the group order, we can get more accurate. But here on the bottom, the calibration error is more so stagnant. So the lesson learned here is that incorrect or extrinsic equivariance can hurt your model calibration, but having correct equivariance doesn't seem to improve your calibration in any way. Another cool thing about this result is it's consistent with the previous studies. I'll mention also that the different lines are under different levels of point per function convolution. So essentially just injecting noise to make the problem more difficult so that we can study this behavior in terms of different accuracies and under different confidences. You know, if you're adding more noise into your system, then you're hoping that your model is more uncertain in its prediction. So that was the motivation by adding different levels of point per function noise for doing this. Yeah. And the cool thing about these plots is the sort of the U-shapes here, but not seeing that trend at the bottom. One is that it's consistent with prior results, but it makes sense in the context of your regression error has a lower bound. That was a known result from another one of the papers from Robin's group related to the action of the group, but the expected calibration error doesn't, because remember that when we define it in terms of an absolute value, and I can always, and since f is something that's arbitrarily expressive, I can always find an f and h such that they're it's perfectly calibrated. So for one of our final experiments, we study if equivariant models can better disaggregate different types of uncertainty. So broadly speaking, you can decompose your uncertainty into aleatoric uncertainty, which is something inherent to the data. You cannot reconcile it with even an infinite amount of data because there's something inherently probabilistic about the process. So the sort of best you can do is hope to capture the distribution of it, potentially by fitting a mean and a variance. And on the other hand, you have your epistemic uncertainty, which is uncertainty inherent to the model, its inability to generalize from finite data sets. So yeah, we looked at this on a variety of Q9 data artifacts. For example, here we're predicting the dipole moment using graphical networks of similar size, but one has E3 invariance and the other doesn't. And we looked for what we called aleatoric mean. The idea was that for a system whose ground truth is given by physics, which, and more specifically chemical physics, where we should be able to solve for very high precision what the dipole moment should be, then all of the uncertainty should be with the model, and it shouldn't be with the data. And if the model is saying that there's data uncertainty, there's some sort of bleeding going on between what the model and data uncertainties are, it can't disaggregate them effectively. And so we're studying this with an equivariant model and a baseline. And so far, we haven't found any evidence that one is pathologically worse in how it bleeds than the other. Also note out the sort of bounds on the x-axis. It does know that it should be having uncertainty mostly with the model, but there is a slight amount of what we're calling bleeding on this half, about a quarter of the amount of the model uncertainty. So yeah, and this is an example where you're predicting a scalar value output, which is just the dipole moment in units of the pi, but returning from our sort of our running example from before. We can also do this for vector value mean and variance predictions, as we've done with the spectra. So here we're saying a similar thing. We're trying to predict a spectral line, and we know that because it's sort of, we know from intuition from the underlying the quantum mechanics that we should be able to, if we were to go out and solve it instead of using an emulator, we should be able to pick the spectral line sort of more precisely. But what the model is doing is it's conflating these high frequency signals that are real information from physics with noise. It thinks it's noise, so it's giving it very high aleatoric uncertainty. So in this case, our equivariant model is suffering a lot from bleed. And so far, we've found no evidence that the bleed is more severe for a graph neural network of similar size. It can be sort of hard because for an apples-to-apples comparison, you want your models to behave sort of similar in accuracy, but maybe it's the confidence that they get far apart. And getting a model even this good, well, without equivariance is tough. So it is hard to do an apples-to-apples comparison. But the idea on those certainty here is that our equivariant model does exhibit some sort of always sort of tweeting. So it's a thing that you would want to correct for. The last thing I'd like to note is that Boston Symmetry Day will be on March 31st. The Geometric Learning Labs led by Walter is very active in organizing. I think a lot of people in the audience here today would be interested in attending. I have left a link on the screen here for people who are sort of interested in going. Yeah, if you have any questions, let me know. You can contact me on the email and on this website, and I'll be looking for a graduate institution soon. So maybe I'll talk to you guys all again soon.
Thank you. Okay. Thank you, Eddie, for a great talk. Are there any questions? Upstairs or on Zoom? Any questions?
No.
Yeah, sorry. She was first.
Hi, thank you for the nice talk. So with the data from the interferometers, like you can also have like 3-dimensional astronomical data, right? So
Yeah.
you have spectrum and also like X and Y resolved information. So I was wondering if you could also use this kind of method to actually classify.
Yeah, I mean, you can sort of, in our regression example, we're thinking about it as a line for simplicity about how it's getting the sort of uncertainty correct. But if you had like, for example, noise over an image, you can sort of calculate the same calibration error just by taking your 2D image and, taking all the columns of it and sort of concatenating it into one vector and comparing it to the actual prediction image and doing the same thing, taking all the columns in your image and concatenating it to a single vector and then comparing. So even if you have a output instead of like Rn, it's a 2D thing, Rn by n, you can always reduce it to a sort of linear case in order to study it, at least in terms of our formalism.
Without dimensionality reduction, it might not be possible.
Well, you're just reshaping the
information, right?
well, you're just reshaping the vectors. You're not changing anything with the values of the form.
There were two others.
Great talk. So kind of a similar question, how does it scale dimensionality, right? So like, for instance, you were showing how a few molecules and its behavior, what happens if you have lots of different molecules who all have very similar rotation signatures and things like that? Or in the case of galaxies, what happens if you extend that x-axis out to infinity? How do things behave? Do they scale? Does it, for instance, do the errors stay relatively static, or do you see any other type of weird behavior?
Do you mean like how? Sorry, can you say a little more? Do you mean like how it scales with other things in your data set, or the size of your output?
I guess size of the output, right? If you like, for instance, the galaxies, right? You have the number of rotation. You have the number of rotations that you're considering, right? I think you
The group order.
Yeah, the group order, exactly. Yeah. Does the behavior of the model kind of stay static all the way out to infinity, for instance?
So yeah, if you extend the group order infinitely, you do sort of plateau after a while. The benefits of extravariance can sort of be limited. The other thing that you can sort of think about is at certain points, alias effects start to take into account. Like,
That's kind of what I was thinking of, yeah.
Like what if I'm going up to like D12, so like 360, like what is like a 70-degree rotation mean on like a 3x3 matrix? It sort of starts to lose meaning. So yeah, and in fact, convolutional networks, even without the equivariance, you sort of get the translation bit of it for free. But because of this alias effect with a very small kernel and then a pooling layer, this can actually break the translation equivariance. There's a paper called the Lee derivative for measuring learned equivariance, and they show that even like your supposedly perfectly equivariant models will struggle due to the effect of these pooling layers and aliasing. So this plateau will extend out for forever. Once you get to 12, or even lower, you do start to see the effects of group order start to level out.
Yeah, thank you.
Thank you, Eddie. I'm just trying to bring this down to some practical things,
Sure.
Especially for the non-experts here, including myself. So, and just following up on what you just said regarding convolutional networks being invariant to translation. So the first part of the question is, does that mean that if you've trained your convolutional neural network on galaxy images on which the galaxy is always at the center of the image, and then you're going to try to predict for images in which the galaxy is offset because it's been translated?
Yeah.
I guess the invariance means that you will still get it right because the CNN architecture is invariant to the translation. Is that correct?
Yeah, so the specific bit of nuances is like I take my 3x3 grid in my original matrix, and then I move it to the right 3x3. And when I put my convolution over it, it'll get to that grid later. So we'll end up putting the output convolution result one block to the left. But if I do something like adding a max or average pooling, that takes your equivariance to invariance. So when we say CNNs get the sort of invariance for free, we mean we get the equivariance for free. And then we use a pooling layer, which means that the feature extracted is invariant.
Thanks. And then the second part of the question is, so if you wanted to, what are strategies to add other sort of, so suppose you start from a CNN architecture and you wanted to make it also rotational invariant. What are strategies to actually, design equivariant or invariant, systems like neural networks that take into account particular symmetries, on practice?
Well,
Thanks.
then the good news is that a lot of this is sort of already done for us. What it amounts to is solving a linear system. So you have your convolution kernel, and it's signing of your thing. What we do is we constrain the weights to be related to each other in a certain way. Like maybe the bottom left and the top right are shared. Specifically, it's weight sharing. If we configure the system in such a way, then we get the equivariance for free. And there's a variety of libraries that implement this for you, such as E2SCNN. So the short answer is that it boils down to solving a linear system about which kinds of convolution kernels will actually give you the equivariance, and that's sort of already done for us.
Thanks.
A question?
Yeah, thank you very much. This was a very, very interesting talk. I have the question related to whether there are cases where the prediction and the uncertainty do not follow the same variance. Because I was thinking of a case, for example, if you have a simple network that just predicts, for example, the position of a galaxy, and with preprocessing, you always move, for example, the position to the center, then it's invariant under rotation. However, for example, if X and Y positions are correlated, then it's not invariant under rotation for the uncertainty. And I was wondering, whether there are cases like this, or whether this behavior is even desired, or sometimes whether this depends on the choice of the coordinate system.
It's definitely desired. I think the field of work that most actively tries to address this problem is this idea of relaxed equivariance, maybe under a certain limit, or I'll use a different example. If we're doing working with crystals, for example, maybe our invariance property falls apart under a certain temperature. So at that part, maybe one of our invariant predictions sort of falls apart. So that's the my work that mostly addresses that problem or conjuring work. The other thing I'll also say is that it's something I'm currently working on, is trying to find an analogous lower bound. But it can be sort of hard with the calibration error formalism. So instead I've been reasoning about it in terms of coverage. I'm getting closer to that answer. But what kind of bounds you can predict if your variance or covariance prediction is constant, but your mean prediction is invariant or equivariant. So the long story short is that it's something I'm exploring currently, but haven't come to a conclusive answer on.
I actually have a second question now that the slide is up. So typically, if you do classification with neural nets, what you assume in the data is that there's a single, or in most cases, a single correct answer, right?
Yeah.
But in practice, this is not necessarily the case. For example, in your case, I mean, if you have these variation with the PSF convolutions, then I guess you should also adapt like your reference data set, like, I don't know,
Yeah,
apply the PSF convolution to the actual data and then let like people re-annotate, and you will end up with a possibly like with a very different distribution, right? The question is whether there are approaches how to take these, like
right.
the uncertainty of the ground truth, let's say, like into account, and how does it translate into the uncertainty that you actually get?
Yeah, so to rest the audience, the idea here might be like the distinction between like a smooth round and an unbarred spiral might be kind of arbitrary. In other words, I can think of like there's not a ground truth answer about which either if a galaxy is smooth round or an unbarred spiral. So really, I don't want to look at the calibration for the highest label. I want to look at them for several labels, and there are metrics like that for the purposes of the study I'm working on. I've been focusing just on the case of one unambiguous correct answer, just for the sake of adding assumptions to the math to make the proof easier to work out. But it's definitely an object of future work to see how this would extend to calibration error over multiple classes.
Okay, thank you.
All right, anything online? No? Okay, so if there's no more questions, what's that? Oh, yeah, please write your name on that piece of paper. And let's thank Eddie again.